Hi, I'm Dave Lenrow. I need to take a quick moment to mention that although I work for Verizon, I'm not representing Verizon here today. I'm representing my own personal opinions and experience. And so today we're going to talk to you about what is 5G and why does it matter. Next slide, please. And beyond that, I'm going to go on and tell you why, in the context of 5G and why does it matter, why building the service mesh control plane will be among the most impactful work in tech in the coming years, and why you should all be super excited about the project you're all working on. And so I want to start by saying that I'm a digital guy and a software guy and a packet guy, and the early days of wireless telephony were not at all interesting to me. Like, we went from sort of 1G to 2G to 3G. It was all about analog and radios, and I'm not particularly interested in those topics, but many of you may have felt the same way, and I just want to say 5G in particular is really different. It's all about software architecture and packet-based things, and absolutely fascinating for people that are interested in that technology. And so 5G is faster, and there's certainly an element of that, but a lot of the big exciting things about it don't exist in the radio layer. And you can see here on the left-hand side of this diagram, there are really kind of four major sections of the topology that are interesting. And the RAN describes the radio area network, which is out where the cell towers are and away from the traditional data centers. And so a lot of what's new and interesting in 5G is that we're putting programmable digital computer technology out at the radio towers and in the radio network, and that changes things entirely. Edge computing is suddenly a part of the telco network where it was not previously. And one of the big new technology components that's introduced with 5G is called network slicing, and includes the idea of having sort of a virtual mobile network available to a closed group of people that has specific service level agreements for security things and performance things and latency and things of that nature. And so rather than kind of one giant monolithic best effort looking network, you end up with several small overlay networks that each have their own properties. You could imagine there's an expectation that this will grow to a place where you might have a Netflix slice for streaming movies and a high quality corporate video slice for two-way real-time video, and Walmart employee slice for people working for a giant corporation, things of that nature. And so that's going to allow telco providers to sell a higher level, higher value service. And it's going to allow telecom service consumers to have all kinds of new services they never imagined. In addition, the locating compute at the edge can reduce latency to the end users and the workloads, and enable all kinds of new use cases and customer experiences as we think about it from the telco perspective. And the fact that this network is being standardized in terms of what are the components and interfaces and how do they talk to each other is necessary because of the scale and breadth of deployments that are expected. Number of endpoints is going to grow by an order of magnitude, and bandwidth is growing, and all those other things. So software architecture is starting to matter a lot more as the network evolves. It's much less about dedicated telephony specific appliances and much more about general purpose compute. We're going from hardware defined to software defined in a lot of cases. And in addition, IoT and kind of the next several billion devices that are coming onto the network have support for their unique needs. So there's a lot in 5G that's software based and packet architecture, and we're going to take a look at some of that today. The next slide, please. So this is kind of a big high level picture of the 5G architecture, and ignore the fact that it consists of lots of strange 3- and 4-letter acronyms that may or may not mean anything to you, but notice that it's very well defined architecturally in the sense that there are clean separation between the control plane and the user plane or the data plane. It's based on kind of a service-based architecture. Networking implementation and details get moved out of the specific tenant workloads that implement the network functions and get moved into the service mesh where they can be applied consistently and be considered part of the platform rather than part of the application. So each one of these dark boxes represents a particular component in the 5G telephony architecture. The idea is that inside of that box, the implementer can do essentially anything they want, but the interfaces to the particular function and the interoperability between the functions is very well defined by organizations like the 3GPP and the ETSI organization. And so cloud native functions implemented as containerized workloads are what most people are building for the implementation that lives inside of each of those boxes. And again, the really interesting piece of this is out in the radio area network, where unlike a traditional data center, we're very constrained in terms of real estate footprint, power, cooling, all of those things. We're not able to kind of throw unlimited CPU at scaling out problems and solving them. And so for that reason, at least initially in 5G, the software architecture and the container orchestration implementation out in the radio networks ends up having really, really difficult performance requirements to make the real-time requirements that are built into the 5G protocols. And for that reason, that data path continues to be a little more hardware defined. A lot of people are deploying a FPGA-based SmartNIC with, dedicated silicon to designed to convert radio packets into something we can use on traditional IP packet networks. And so there's kind of a piece of the network that looks more hardware defined and super optimized in the data plane. And then as you get deeper into the network, we're able to take advantage of more compute availability and more cloud native scale out types of architecture in order to manage load. If you go to the next slide, please. So some of the key platform requirements for building a 5G telco platform today are kind of first and foremost multi-vendor. Now that we have well-defined network functions and interfaces between them, it's finally possible to make these products fungible in a way where you could buy something from one vendor and decide in a different region that you could deploy the equivalent from a different vendor and find that you can swap them out interchangeably without undue difficulty. In addition, as I've talked about, there's this whole real-time component, super fine-grained kind of microsecond timing synchronization that has to go on throughout the radio network that leads to some really difficult performance requirements. Workloads need to be mobile. A single CNF might run on a single worker node, or it might be spread across a cluster, or it might be spread across multiple clusters. And all of those scenarios need to be managed smoothly. Again, getting the networking outside of the containerized network function is really important. The platform wants to have the ability to change the networking implementation as bugs get fixed and vulnerabilities get closed and new technologies get invented. And we don't want to do this by going to 27 different CNF vendors and asking them all to make major changes and try to synchronize all of our schedules and deploy that. We'd like to be able to put them behind an API where they ask for services rather than defining network behaviors, and the platform provides those services in a way where we can change the implementation. For example, we could switch from today's generation of encryption ciphers to something that's quantum safe by throwing a switch and pushing different sidecars implementations out next to all of our network functions, rather than having to ask all those vendors to go back to school and respin, retest, redeliver, re-onboard that entire cycle. And in addition, we want to have encryption and strong authentication between the network functions as a ubiquitous universal platform service, not something that's implemented in a piecemeal fashion and in some places, but not in others. And we need to really move to a place where end-to-end means workload to workload, not middle box to middle box. And so if you look at the next slide, please. People who are familiar with microservices and service mesh will see kind of a similarity. The picture on the right is not actually a network function. It's kind of a generic description of microservices and their interconnection and their relationship. But if you kind of lean back and squint a little bit, you notice that it looks a lot, topologically, it looks a lot like the left-hand diagram, which is the 5G architecture. And so essentially, the microservices within the Kubernetes clusters have interfaces that are not necessarily as well defined and don't have super strong contracts that are enforced by standards. And in a lot of ways, the service mesh becomes the tool that allows for easy interoperability and fungibility within that. And you could easily imagine sort of the same thing happening if you think inside every one of those functional boxes in the 5G architecture is a bunch of microservices connected by a service mesh that you can also think of, it's as a sort of a recursive or a fractal pattern where we have the same sort of service mesh-like connectivity between all of the 5G nodes and a similar kind of behavior that needs to be supported. And if you go to the next slide, please, I want to talk about what it is in particular. Here's what Istio looks like when you insert it into that same picture. So again, these are functional blocks. They're not describing topology. If you look at, for example, the SMF, that might be, again, running on a single worker node. It might be running across a cluster, or it might be running across multiple clusters. So the actual low-level ability for these things to communicate in a secure way with consistent policy, again, needs some additional tool on top. And as it turns out, service mesh is just as valuable and provides all the same functionality at this sort of macro layer between these different functions as it would within the functions to control their own internal behaviors and housekeeping. So in the next slide, we'll see what is it that we get from Istio that's so valuable in this telco 5G platform that we're building. And first and foremost, we get enforcement primitives to build zero trust. And to oversimplify, zero trust is a combination of really strong identity for all of the users and workloads and devices and packet flows, and then strong privacy between those nodes when they're utilizing those network services, and the option to transparently and consistently encrypt all traffic across the entire mesh with MTLS is kind of the first and most valuable component of that technology. And then the fact that the sidecar itself is adjacent to the operating system and application space rather than one hop away in a middle box ends up in a scenario where you have much better context to build strong identity by looking at process tables and socket tables and things of that nature. Next slide, please. So in addition to that, you get the strong observability and visibility features and things that allow you to debug inside functions that are otherwise opaque. And finally, the powerful layer 7 traffic management that you're familiar with. Next slide, please. So Neeraj is going to talk a little bit about architecture options.
Thanks, Dave. This is a wonderful overview on 5G and its application across industries and how Istio plays a role in building a platform like that. What I want to talk about are the various architecture options you have when you're using Istio in your platform. Istio itself is quite extensible, and for meeting any particular requirement that Dave talked about, you have various options. To understand these options well and making sure that you're meeting a requirement is the key architectural decision that you have to make. Similarly, I'm going to share some of the learnings that we have come up with together while building a platform using Istio at its core. So first off, I want to talk about is how to achieve tenancy or multi-tenancy, which Dave said was one of the most important things. So in a 5G platform, you will have container cloud native functions or CNFs from multiple vendors. You want to make sure they can be deployed in a way that they share the same underneath resources, but they have the control so that they can apply policies uniformly while still retaining control for each vendor's CNF. At the same time, the policy enforcement engines, whether it's proxy or something else, does not have penalties for performance where data flowing through one of the performance policy enforcement engine for one network function affects the performance of the other, right? So in Istio and in particularly also in Kubernetes, the way to achieve this tendency is to deploy your network functions or CNFs at a namespace level. So what I mean by that is you can have two CNFs, AMF and SMF. Like Dave said, ignore that these are 3-letter acronyms, but they just provide functions. So in this case, it's accessibility and mobility function, talking to session management function. So each of these network functions are microservices by itself. So and then inside, if you open them up, they will look something like this. You have a front end talking to an app, which is all part of AMF. They will have its own database. Similarly, SMF will have a front end application and its database. Now, you want to make sure that the traffic between these network functions at a inter-CNF level is at least encrypted with solid workload identities that Dave was talking about. What we found that you have a hybrid environment here, actually, when you try to achieve it with Istio. Not all vendors will be willing to add sidecars in their CNFs. They are going through various phases of migration. Some of them are lifting and shifting. Some of them have still not tested. So what you end up having is actually an architecture like this. You have sidecars in some of the network functions, and in the other network functions, you won't have sidecars. So what you can do is you can add an ingress gateway for those network functions, which can provide the same primitives for encryption, and then help you migrate later when you are adding sidecars to all the components within a particular NF. For example, over here, you might be adding sidecars eventually to all the components in SMF. So now in this architecture, which seems simple, there are 2 or 3 key challenges you will face when you're building it. First is you want to make sure you have strong identities that you are attaching to these proxies. So for the AMF, so the AMF front end has a sidecar, so the sidecar gets the AMF identity. For the SMF side, you want to have the SMF identity attached to the ingress gateway. The issue here is in Istio, for ingress gateways, normally the northbound interface or the interface exposed to the outside world is not managed or cannot use the Istio generated certificates itself. So this is something we had to augment to teach Istio to consume its own certificates. Secondly, we also found that as Istio's architecture evolved and we went from Citadel to SDS, the Istio generated certificates were themselves not available as secrets, which can be used easily by the ingress gateway. But once you are able to augment Istio and make sure that the certificates that the control plane creates is uniformly consumed by both the sidecars and an ingress gateway northbound interface, you can easily migrate all your CNFs to later use and inject sidecars, right? So from this architecture, once you have the identities established and uniform PKI infrastructure to rotate certificates, you can have strong encryption between the entities which have sidecars or sidecars to ingress gateways. And then as you evolve your architecture, you can add you can get rid of the ingress gateway, you can add the sidecars in all of these components, attach stronger identity to the sidecar workload, and then you have encryption in a much better way, right? So this is the benefit you get by having the architecture. You can create uniform policies, where in one end you might have sidecar, in the other end you have ingress gateway, but you can move the same policies forward as you are able to add and introduce sidecars to each and every component. So the second thing that I want to talk about is legacy network functions, and how to make them talk to CNFs in the mesh. This is a common problem that you will have whether it's a 5G platform or whether it's an enterprise application. You will have legacy functions that have to talk to containerized modern applications. So in this case, you have UDM network function, which might be on a virtual machine that wants to talk to a CNF, which is in containerized world. So the issue here is as soon as you add the sidecar to SMF, obviously you want to do encryption. And when you try to do encryption, this communication breaks because the virtual machine cannot talk the language that the sidecar is talking over there. It doesn't understand the SPIFFE-based SANs. It doesn't know how to get the certificates. So there are a bunch of options here to solve this problem. First off, this is the Istio community recommended way. So you can add an Envoy sidecar proxy in your virtual machine and extend your mesh to include virtual machines. So it feels like your virtual machine is participating in the mesh as if it's in the containerized environment. And then the control plane is transparently managing the certificate lifecycle and identities for both the sidecars in the virtual machine and also injected it as part of the pod in SMF. Now, if this works for you, it's great. But for many vendors, this won't work because either your VM itself might be running in an environment where you don't want to change it, or it might be running in SRV or DPDK enabled environments where you can't actually inject Envoy sidecars that easily. So in that scenario, you might end up with a architecture like this, where you have a dedicated egress gateway, where the egress gateway will be used to transparently upgrade the connection between UDM and SMF. Again, in here, you will have the same problems that we had when you were trying to add the ingress gateway between a sidecar enabled pod and then a pod without the sidecar. In the egress gateway, the connection to the outside world needs certificates for encryption, and by default, it cannot use the Istio enabled certificates. But if you are able to extend Istio, you can have uniform certificate management for both legs of this traffic. The downside of this architecture is obviously the communication between the VM and the egress gateway is still unencrypted. So another way to fix that is actually enabling the application to talk TLS directly. So in this case, you want the virtual machine to participate in the mesh by getting the certificates and the credentials directly from the Istio control plane. Again, this is easier said than done. In the older versions of Istio, where there's Citadel was creating secrets, and you can have the virtual machine get the secrets based on an API or mount it as a file somehow, and get those credentials to create a TLS-based connection. With SDS, it gets difficult. So either you have to preserve the behavior of Citadel to create those secrets just for these use cases, or go some other route. Additionally, most of the legacy applications don't really understand SPIFFE-based certificates. Even though SPIFFE is great for creating identities, Istio by default only will add SPIFFE identities in SAN. So if you want these virtual machines to participate in TLS traffic and understand the certificates, we had to go ahead and augment Istio to create SAN identities which are based on DNS, so that these virtual machines and legacy applications can understand and participate without a lot of changes on their end. So these are some of the options that you will have that's applicable in a 5G world, but also these are the same problems you might have in enterprises. Moving on. Yeah, so basically in this case, the UDM identity is attached to the UDM virtual machine itself, and it's managing the TLS directly. There are a lot of tuning that you might have to do in Istio itself, as Istio has a lot of configuration knobs to make sure you're meeting the 5G requirements. So this is some of the things that I would recommend you do. First is to make sure you use CNI so that you're not having any escalated pod privileges. By default, Istio adds a Istio init container, which runs as an init container, which sets up the IP table rules for you. But for it to run the IP tables, it has to have escalated privileges. In many of the environments, especially like OpenShift, you might not be allowed to have those privileges. And in those modes, running CNI is better. It requires less privileges and it's more secure. Secondly, you should integrate with your own PKI minted intermediate certificates. By default, Istio will work and use, and it will generate a root CA that will use for minting all the workload certificates. Uh, Creating your own intermediate certificate authority is much better because it allows you to also extend your mesh easily by using the same trust across different clusters or different sites, which, as Dave mentioned, is important in 5G, as all of these network functions, there's no way to fit them in just one cluster, right? You should be enabling ECC certificates. So this is one of the functionalities that was added by our team in Aspen Machine Open Source recently. Um, uh, Whenever we talk to 5G security architects, they will always say, we need something like this. And I'm glad that now Istio supports it. You should be able to configure your workload certificate TTLs. By default, Istio comes with around 90 days of workload certificates. You should be able to reduce the time. This is again important because there's no way to directly revoke workload certificates in Istio. So having a shortened TTL can help you work around that problem. You should also be looking at enabling your strict mutual TLS. Istio will by default use auto MTLS, which was created for migration purposes. But if your aim is to have strict zero trust and have all traffic between these CNFs or inter CNF traffic encrypted, you should have strict mutual TLS and have traffic failures rather than policy violations. Another aspect is if you want to secure down your network, you, especially for outbound traffic, you should be looking at using dedicated egress gateways. There are policy primitives to enforce outbound policies, but those outbound policies in Istio are enforced at the client, and you should not be just relying on well-behaved clients. You should enforce the outbound at an egress gateway. You can use the Istio egress gateway or a more capable big IP or something like that if you want to use, but it's always better to insert that in your network rather than relying on client-side enforcement. Moving on, some of the other things that we had to tune to make sure Istio is meeting the 5G requirements is we needed to augment tracing to surface some 5G specific tags. This functionality was also again added by our team in Aspen Machine Open Source Istio to make sure when the tracing is enabled for this CNF traffic from one CNF to the other, you have the tags that is surfaced by Envoy for HTTP and bunch of other metadata, but it also has 5G context in it. There are specific 5G headers that each of these network functions propagate, and you want to make sure that context is in those traces so you can actually understand what's happening when traffic failures happen. You should be able to optimize your HTTP2 stream and connection settings. This is all more important for network functions like service communication proxies or SCPs, which are a critical part of 5G flow where all the traffic goes through. Interestingly, we had to optimize HTTP2 stream and connection settings, not just for the outbound, but also for traffic between the pod and the workload on localhost. Similarly, you want to scale your proxy threads or concurrency settings depending on the workloads, and those work depending on your throughput. And those throughputs vary for different workloads and different network functions. So these are some of the things that I would recommend tuning in your Istio environment to make sure you have a secure 5G platform, you have secure Istio so that you are reliably having your enforcement, policy enforcement, and encryption that is so important, as Dave mentioned. Some of the learnings along the way, or I can say some of the challenges that we had building a 5G platform is the Istio architecture itself evolved, moving from Citadel to SDS, even though it's more secure, meant we had to rethink how you can enable some of the communication patterns I mentioned before. Moving away from Helm as a primary means of lifecycle management also caused some churn because many of the vendors itself normally use Helm for their microservice deployment, and using Helm as the common language simplifies a lot of things. So I'm glad in Istio 1.8 we were able to reintroduce Helm as primary means for installation and upgrade for Istio, along with the other supported options as Istio CTL and operator. Spiffy only certificates can itself be challenging, especially if you want legacy workloads, legacy clients, or if you want to have regular HTTP clients, they don't really understand SPIFFE certificates. They want DNS in the SAN. Configuring workload certificate TTLs should be a simple job, but sometimes those options are hidden. So you might have to figure out a few layers before you understand how you can configure them reliably. As ECC certificates was added later on, you might have to migrate from RSA to ECC. This migration is quite difficult to achieve with zero downtime. It can be achieved, but it might take few iterations before you can get there. We also realized some of the critical headers for unauthorized traffic. When the proxies were returning 401, they were missing headers like www authenticate headers, which many of the network functions relied on. Tuning per proxy concurrency setting was added much later in Istio. Before, you could only enable proxy configuration for the concurrency at a mesh level, which works for most use cases, but for network functions, some of them have critical requirements around concurrency. And like I said, consuming Istio-generated certificates as gateways is not very trivial to do. You have to make a lot of changes to make that architecture work. One thing that I want to talk about is you can think of 5G having well-defined contracts and APIs like Dave mentioned, but there are still a lot of requirements that require us to go beyond Istio. When I say beyond Istio, you might have to augment Istio, or you might have to add other components to make sure that communication pattern is working. So there are legacy protocols and other telecom-related protocols like Diameter, SCTP, and GTP, for which currently there is no support in Envoy. So you might have to add a proxy like Big IP to make sure these translations happen before the mesh traffic can begin. For high-speed data path traffic, which relies on SLRV or DPDK, there is no good support for adding Envoy right now and making sure you have service mesh in these use cases. Customizing workload certificates is another extension that is good to have, where you can have 5G metadata in these certificates. So you have cryptographic proof that is used for encrypting traffic and also presenting a lot of valuable metadata about the workload and the network function. And then similarly, you have to build out a way to have multi-cluster, multi-site visibility so that when the traffic goes from one mesh to the other or from one cluster to the other, you can understand what's happening. One of the last things that I'm going to talk about is deep packet inspection, which is the capability where service providers are able to recreate failures in the network by capturing traffic at full fidelity between network functions. Now, this is an important feature for them, but adding a service mesh or adding a sidecar proxy and moving the encryption can often break it. So I'm going to quickly go over the same example and see what happens. So you have AMF talking to SMF, you have encrypted traffic. In the traditional world, this traffic will be tapped by optical taps and sent to network analyzers for getting full fidelity captures. But since this traffic is encrypted now at the mesh, you can't really decrypt it. This is because it's encrypted with perfect forward secrecy, and it's not easy to maintain session keys for all this information. Additionally, these taps don't really work at layer 7, so you are missing critical HTTP2 related transaction data. And you don't really have reliable contextual data about the Kubernetes namespace, for example, the metadata about the app labels. You just have ports and IPs, which itself can change. So the only way to really make the same capability work in the new world is capturing these packets before they get encrypted. So this is like moving some functionality that used to be in these middle boxes and moving them closer to the workloads. And this is where I'm going to hand it back to Dave, who is going to tell us how he envisions the network topology changing with the addition of sidecars to workloads. Over to you, Dave.
So next slide, please. So today, and traditionally, we had what you could call sort of a fat network and skinny endpoints. Inside of the network DMARC, there were all kinds of middle boxes with special dedicated function, and you could sort of compose service chains by taking multiple hops through some custom path through that network. But as Neeraj showed, as soon as you move encryption into the endpoint so that it's truly end-to-end. You've now disabled visibility into all of those packets in such a way that you end up wanting to move things like DPI out of there as well. And then increasingly, the goal of large-scale cloud network operators is to be able to move to a world where you have a smarter edge, a fatter edge, if you will, and a dumber or skinnier transport network in between. This allows you to reduce costs and to, continue to have a completely hardware-defined data path inside the transport network, where you have to move things at kind of multi-terabit speeds, but a lot of the high-touch packet features can all leave that network and end up running at the edge and becoming software-based. And so the kind of ultimate evolution of that notion is you could have sort of all of the packet processing that's not very specific to connectivity and capacity all moves out into the edge proxies, and the only thing left in the network is sort of connectivity and bandwidth. And then finally, if you go to the next slide, taking a look at what's happening out there in the world, and today there's Envoy proxy projects for both popular mobile operating systems, for Windows, for every flavor of Linux, for everything else. If you kind of extend all these concepts, you could imagine a world where there's a sidecar proxy of some sort running Envoy or something like it in essentially every operating system instance in every device, from your watch to your car to your factory floor to your cornfield. And I want to let the people know here that leave you with an understanding that Istio is one of the key control plane technologies emerging in service mesh and has the potential to become a global scale policy framework that will be literally everywhere. So that should get you super excited to go out there and build out more capability and more scale that we're going to need in Istio. And want to leave you with that vision of service mesh is going to eat the world, and Istio's got a good chance to be the control plane for that.
Awesome, Dave. So with that, I think we might have few minutes left for